Hello everyone, welcome back to Computational Nanophotonics videos. I'm Josh, and today I'm going to continue talking about the Meep FDTD software package, and we're going to be using Meep for waveguide simulations. I'm also going to be doing a quick introduction to MPB for waveguide mode calculations. So in this video, we're going to talk about what is a waveguide. We're going to do a very informal introduction to waveguide modes. We're going to talk about eigenmode solvers and do a demonstration with MPB. So just quickly here. So MPB is the MIT Photonics Band software. So it's meant for computing the band structures of photonic crystals. But in this video, we're going to be using it for solving waveguide modes. If you have Meep installed on your computer, you most likely already have MPB installed. So if you went through my last video and you installed Meep with me, then MPB should be installed on your computer already. So after that, we're going to talk about waveguide simulations with FDTD. So we'll talk about eigenmode sources and eigenmode monitors. And then after that, we'll do a demonstration of waveguide simulations in Meep. So an optical waveguide is essentially just a wire for light. It allows us to confine electromagnetic waves to a very small volume, and it allows us to have that wave travel in that confined space over these long distances. So waveguides are essentially by themselves lossless. However, the materials that make up the waveguide are usually not lossless. So essentially the light can travel through the waveguide over a long period of, or over a long distance, but over that distance, just because of the losses that make up the material, that light will decay. So this is what the light looks like as it travels through a waveguide. So here I'm simulating a waveguide using lossless materials, using FDTD. So in the middle here, we have some sort of core material, and it has a larger refractive index than the material outside. So on the top and the bottom, we have what we would call the cladding material. So we have a core in the middle and cladding on the outside. The core material has a larger refractive index than the cladding material, and that allows light to just travel through that core material. And again, if the materials were actually lossless, it could travel forever. But unfortunately, there is loss inherent in materials. So yeah, that is what a waveguide is. And waveguides are based on the concept of total internal reflection. So here again is what a basic waveguide looks like. So in the middle, as I showed in the last slide, we have this core with a refractive index N2. And then on either side, we have the cladding, N1 and N1. And N2 is bigger than N1, which means that there's going to be a critical angle for which light traveling in the core can hit the cladding, and there will be total internal reflection. So all the light that hit the cladding is going to get reflected back into the core. So if we can inject light with that angle, that light will just total internal reflect all the way down the core, and we'll get pretty much lossless propagation. So yeah, as I mentioned, if we were able to put light inside the core so that the angle that it hits, so this white arrow kind of just shows the optical ray. So if that ray can hit this interface with an angle theta that is greater than the critical angle, then the reflection coefficient is 1, and then there is no loss at this boundary. So the light can just reflect back and forth, all the way through the waveguide forever. So yeah, lossless propagation. Again, though, our material, our N2 material, will have some loss in reality, so it's not entirely lossless. And yeah, waveguides can have many different cross-sectional shapes, sizes, and materials, depending on what you want to use them for. I won't go into detail here, but here's some pictures of different waveguide shapes. In my experience, I've usually just worked with buried waveguides and rib waveguides, but these other shapes, you'll see them in the wild. But what's important with these waveguides is that in the propagation direction, so that's into the screen here, the waveguides look uniform. And waveguides allow us to create photonic integrated circuits. So I have a picture here or a schematic of a photonic integrated circuit. So all the blue lines that you see are waveguides. So light, laser light, is injected into the waveguide over here, and that light travels into a modulator here. That light will get split, and then there's a amplitude modulator here, a phase modulator here, all these modulators that operate on the light. But essentially what's happening through all these modulators is that information is getting encoded onto that light, and then that information can be sent to somebody else using some fiber optic cables, which can transport that light over long distances. And then that fiber optic cable will then inject light into this other photonic circuit where that information is decoded so that this person can read the information. So Alice owns this encoding circuit up here, and she sends information all the way down, and then Bob can decode that information using his photonic circuit. So yeah, photonic integrated circuits, they work like almost like electronic circuits. Not really, but you know what I mean. But they're used in optical communications, photonic computing, quantum optics, and they're all enabled by these waveguides. So to talk about waveguides, we need to understand what the electric field looks like inside a waveguide. So as I said, waveguides are going to be uniform along the propagation direction. So in this movie, you can see that along Y, the waveguide profile doesn't change. And it's because of that that this light field can just propagate losslessly. So because of this uniformity, the electric field along the Y direction is just going to be this complex exponential term. So you can see here, if we were to take a cross section of the electric field along Y, let's just make the video, let's just go over here. So yeah, we take a pause in time, and then we take a cross section along Y. What we would see is an oscillation, right? So wherever you see blue, the electric field is negative. Wherever you see red, the electric field is positive. So we get this kind of sinusoidal oscillation of the electric field along Y. So the electric field along Y just looks like this plane wave term here. Okay, so then the total electric field, the electric field is a function of X and Y, is just going to be this plane wave term along Y, multiplied by some electric field profile along X. So if we look here in our video, we can see that along X, there is some sort of electric field profile, right? The electric field is very intense in the middle of the cladding, but as it goes towards the core, the electric field drops off. So I would guess that this E at X is kind of like a Gaussian, right? It's going to be very high in the middle of the core and then drop off to zero towards the edges of the waveguide. Cool. As you probably have noticed, there's this KE term that I have. So this is our effective wave number. It's the wave number of the light in the waveguide. And it's just given by 2 pi divided by our effective wavelength. The effective wavelength is just the vacuum wavelength divided by the effective refractive index. So the effect of having this waveguide here makes it so that the light can propagate along the waveguide axis almost losslessly. And it has this effective wavelength, which we can see here, right? The distance between one red peak to the next red peak. And that effective wavelength depends on the effective refractive index of this waveguide. All right. So more generally, of course, we're going to be working usually with 3D stuff. So our electric field is actually a function of X, Y, and Z. But again, along the Y direction, we just have our plane wave term, and then we have some sort of electric field profile in the X and Z direction. And here's what that looks like. So I actually simulated this sort of waveguide structure, this buried waveguide structure using MPB, and we'll be doing that later. But here's what that looks like. So we have our core, which I kind of outline with this dashed line, and we have the cladding around here. So we can see that the electric field is very focused in the core. So the electric field, so E at XZ is much higher in the core, and then it drops off into the cladding, as you can see. And yeah, I just wanted to show you what E at XZ might actually look like in a realistic example. So if we take this guess of the electric field and we plug it into Maxwell's equations, We'll do a bunch of algebra and calculus. Again, I'm not actually going to do that in front of you. If you actually want to see what this looks like, I would very highly encourage you. Sorry, just taking a little detour. I really highly encourage you to check out the EM Possible video by Dr. Raymond Rumpf. Yeah, up here, Raymond Rumpf. On the finite difference analysis of waveguides. It's in his series on computational electromagnetics. This is a very good video showing how you can use finite differences to calculate the electric field inside of waveguides. And I actually have used this video to write my own waveguide mode solver. So highly recommended. You'd probably need to start around lecture 9 where he talks about the finite difference method. But yeah, great video. Please check it out. Okay, with that out of the way. So because books and Dr. Raymond have done this already, I'm going to avoid the math and I'm just going to simplify stuff here. In the end, after we plug this guy into Maxwell's equations, we get something that's going to look like this. So we have some sort of differential operator, which will depend on our x and z derivatives. And it's going to operate on our electric field, E at xz. And this is going to be equal to the k, our effective wave number squared, multiplied again by the electric field at xz. So we have some operator operating on E is equal to some scalar value multiplied by E. This is just an eigenvalue problem where the eigenvalue is the effective wave number squared, and the eigenvector is just the electric field. So yeah, again, we started with this this guess of a solution for the electric field in a waveguide. We plugged it into Maxwell's equations, and we got an equation for E at xz. And then we found that that's just an eigenvalue equation. And the solution of this eigenvalue equation are what we call eigenmode solutions. And in general, there's going to be multiple solutions. And so we label each solution by some n index. So if you use an eigenvalue solver or an eigenmode solver, it's going to give you multiple solutions. The most likely, if you're going to be using waveguides, you're probably going to be working with the fundamental mode. So that would be the n equal to 1 mode. But yeah, it is good that you can use an eigenmode solver and get all the modes that are available in that waveguide. Okay. So yeah, an eigenmode solver is just some sort of software package that helps you solve these E sub n's. Sorry, it helps you solve the eigenvalue problem here, and it'll give you the eigenmode solutions for some arbitrary waveguide shape and some arbitrary electromagnetic frequency. It only requires the cross-section of the waveguide, so you don't need to do some sort of 3D simulation. It's actually, for a 3D waveguide, it becomes a 2D simulation, and if you want to do just a 2D waveguide, then it becomes a 1D simulation. And then, yeah, so you give it the cross-section of your waveguide, and it'll return the electromagnetic field profiles for the modes of that waveguide. It'll give the effective wave numbers for each of those modes, and from there you can get the effective refractive index for each of those modes. Right, just to summarize the eigenmode solver, but more visually, you give it the cross. So we want to know the electric field of light in a waveguide. So we know that it's going to look something like this, but we want to know what is En at xz and what is Ke at n. So we use an eigenmode solver to do that. So we just give it the waveguide cross section with the permittivity for the core and the permittivity for the cladding. And then it'll give us that En at xz and the Ke sub n. All right, with that out of the way, we're now going to use the MIT photonic bands, so the MPB package, to calculate and visualize the waveguide modes for a silicon on insulator. Oops. Sorry guys, I went ahead there by accident. Silicon on insulator waveguide. And so a silicon on insulator waveguide, or a buried silicon on insulator waveguide, is going to look something like this. So we have a silicon core, and a silicon dioxide or glass cladding. All right, so let's get to the code. Okay, so like last time, I'm going to be using the Ubuntu subsystem of my Windows computer so that I can use the easy to install Meep package. So the first thing I'm going to do is I'm going to activate the Meep environment that I installed in the last video. So conda activate PMP. There we go. Now I can use Meep and MPB. So here's my MPB script. I just called it MPB underscore waveguide.py. So the first thing we do in this script is we import Meep, we import NumPy, import matplotlib, and then we're going to import MPB using from Meep, import MPB. There we go. And I don't think I need this, actually. I'm going to get rid of this line here. I don't think I need to import that module. That's just old code. Okay, so the first thing we're going to do is we're going to define the core and cladding material. So here I'm just going to be using a dispersionless, lossless material. So here I'm using a refractive index of 3.5. So that should be about the refractive index of silicon in your C-band. And for the cladding, I'm just using a refractive index of 1.44. And this is just your silicon dioxide in the C-band. So right, MPB, it can do it does mode solutions using finite differences. So you have to define a resolution like we did last time. And again, the resolution is just the number of pixels per micron. So here I'm doing 100 pixels per micron. So my step size is 10 nanometers because 100 times 10 nanometers is 1 micron. Okay. So yeah, we need to set up the simulation domain. So here I'm setting up just a box that is 3 by 2. So 3 microns in the X direction and 2 microns in the Y direction. Okay. Because yeah, I'm going to say that my waveguide is in the XY plane for now. I know in the slides it was in the XZ plane, but it's just easier to write code for the XY plane right now. So that's what we'll do. Our waveguide is going to have a width of 0.5. So that's the width in the X direction. And it's going to have a height of 0.22. So that's 500 nanometers and 220 nanometers. Yeah, I guess this should be obvious already, but MPB, just like Meep, everything is in microns. Okay. So to set up the cladding, I'm just setting up an infinite by infinite block of the cladding material. So mp.block is just it gives you a rectangular prism. Because we're just doing a 2D simulation, this is just a rectangle. And again, I set it to be infinite by infinite in the X and Y directions. And then here for the core, I'm just setting up a block with the material of the core. And it's just going to have a width of width and a height of height. Okay. Finally, we need to set up what wavelength we want to use. So I'm just going to say use a wavelength of 1.55 microns. So that's the middle of the C band. So then the frequency is just 1 over the wavelength in Meep. I'm going to be asking for 3 modes. And now I need to define the actual mode solver simulation. So here we're going to just uncomment all this stuff here. So I'm saying I'm going to call the mode solver instance ms. And ms is just mpb.modesolver. And then I'm going to give it the size of the simulation. So that's just given by the geometry lattice. We're going to give it the geometry, which is just our cladding and our core. We tell it what resolution we want, and then we give it the number of bands that we ask for. So, or the number of modes that we ask for. So I asked for 3 here. Next, I'm just going to initialize everything here. So I just call ms.initparams. It wants to know if there's any parity. I believe that has something to do with the symmetry involved. I'm just going to tell it mp.noparity. And I forget what this true is for, but just set this to be true. You can go into their documentation to find out what all this stuff means, but ms.initparams just makes it so that I can just quickly plot the simulation. So that's what I'm going to do next. So I want to plot what the simulation domain looks like. So first I'm going to get the permittivity. So To do that, we just call epsilon is equal to ms.get epsilon. So if we plot this eps, this is just going to return an array of the permittivity values across the simulation domain. So if I plot this epsilon, what I'm going to see is I'm going to see the core in the middle of the cladding. So I'm going to define the x and y axis for the plot. So the way that I do that is I'm just saying np.arange epsilon in the x direction. So the size of the size of epsilon in the x direction. So this will just return a list of numbers 0, 1, 2, 3, 4, all the way up to the shape in the 0th direction. Similarly for y, and then we divide this by the resolution to get the axes in the units of microns. All right, finally we plot. So here we're plotting, we're going to use the contour F plotter with pyplot. Pyplot? Yeah, pyplot. Yeah, that's right. Okay, so plt.contourf, we give it x and y as the first two arguments, and then we want to plot the permittivity array. We dot transpose it so that it's x on the horizontal and y on the vertical. If you don't transpose it, this will be wrong. So yeah. And for the color map, we're just going to use binary, which is a grayscale color map. Finally, we give it a color bar. We're going to save the plot, and then we're going to close that plot. All right, so let's just run this real quick, and so we can see what we're simulating. What did I call the script again? MPB waveguide. All right. So again, we just run it using Python, MPB waveguide.py. There we go. So you can see that it ran some stuff here. And let's just take a look in my folder. Okay, so here's our folder, and you can see that we have our permittivity plot here. So if I open that up, this is what the permittivity of our simulation domain looks like. So along the x-axis here, you can see that we have 3 microns, and along the y, we have 2 microns, because that's what we asked for, a simulation with a simulation box that is 3 microns by 2 microns. And then here in the middle, you can see our core, which has a permittivity of around 13.5. So that's that 3.5 squared. So yeah, this is our simulation domain for the mode solver. So we go back to the code, and now we want to actually calculate our eigenvalues. So to do that, we're going to loop through our modes. So again, we're asking for 3 modes here, so we're going to loop through those modes. And then we're going to use, to get the wave number, which is our eigenvalue, right? We're going to use this find k function. So the first argument, we're just going to say no parity. So don't use any symmetry or anything like that. We give it the frequency that we wanted to evaluate the mode with. We give it the minimum mode number and the maximum mode number. So we're just going to set those to be the same. Mode number +1. So what I'm going to do is actually I'm going to get rid of the +1s because that can be a little confusing. The +1 is only there because Python starts its indexing at 1, whereas MPB starts its mode indexing Python starts its indexing at 0, whereas MPB starts its mode indexing at 1. So we have to kind of offset the loop by this 1. Anyway, so this is the minimum mode number that we want, and this is the maximum mode number that we want. Since we're going to be looping through the modes, I'm just going to set them to be the same. You need to give it the direction that the mode's propagating down. So we're doing an XY plane for our cross section, so the mode's propagating in the Z direction. So we give it 0, 0, 1. It's doing an eigenmode solution, so it needs a tolerance. So we're going to set that tolerance to be 1e -5. So I set that up here. It just needs to be a small number. 1e -5 seems to work. Then we need to give it some guesses. So it's trying to guess a k value. So we're going to give it a k guess. And that k guess, so this is going to be a little weird. But the k guess is just going to be the frequency multiplied by a guess mode. So, okay. So how do I explain this? In Meep, the wave number and the frequency are the same, right? Because if you remember my last video, Meep has some weird units where the speed of light is 1 and all that stuff. So it's just worth knowing that in Meep, the wave number and the frequency are the same. So and then to give it a guess wave number, we just need to multiply. So I should say the wave number in free space. So take guess not is equal to the frequency. So to give it the wave number guess in the material, we need to give it a refractive index guess. So that refractive index guess we're going to call end mode guess. And I'm just going to set that to be halfway between, so n, what do I call this? N core and n clad. So I'm going to say 0.5 times n core plus n clad. So again, so the vacuum wave number is the same as frequency, and then the mode wave number would be the mode refractive index multiplied by the frequency. And we're just guessing the mode refractive index to be halfway between the core and the clad. That's not true. It's just a guess for the solver to use. Okay, cool. We also have to give it a minimum K and a maximum K to search through. So K min, and again, we're just going to use frequency multiplied by n mode min. So n mode min, we're just going to say that the minimum mode refractive index could possibly be is going to be n clad. So the mode refractive index will not be less than n clad. And finally, n mode max, the mode refractive index will not be bigger than the core's refractive index. So then we have K min, K max, which is just this. There we go. All right. So we're going to plug these three guys into our function here. So we have our K guess, which just goes after the tolerance, your K min, and your K max, which I set here to be frequency times 4 before, but K max. There we go. All right. So this here is going to give us our wave number for our waveguide for the mode numph mode. Oh, that's silly. All right. So to get the effective refractive index, we just need to take that wave number that we get and divide it by the frequency. Because again, the refractive index is the wave number divided by frequency in Meep units. Okay, with that out of the way, I'm just going to ignore all the other commented out code for now. I'm just going to run this as is, and we're going to just print nf. Oh, right, nf is an array that we need to define. So here we go. nf is just an empty array, and it's just going to collect the effective index values from MPB. And then it's going to print those values. So let's run this. Okay. There's a lot of printing out happening because it's solving everything. Let it run, let it run, let it run. Oh, wow. There we go. Okay, so it finally solved. If we look at the last line, this here is what we asked it to print out. So we said to print the effective refractive index values. So for the first 3 modes of this waveguide, the effective refractive index values are 2.45, 1.76, and 1.49. Cool. So there you go. So that's how you get the effective refractive index of a waveguide using the MPB software. One thing I'm going to do is I am going to shut off all of that print stuff there. I believe we can do mp dot verbose 0. Is that how let me do this? Let's see. Oh, maybe it's verbosity. So if we do that. Okay, I'm going to reduce the resolution so it'll run faster. So I'm just going to go to 25. So there we go. Now it ran without all that printed out stuff there. So now it ran, and we can just see the effective index values. And you can see now this time they're slightly different because I changed the resolution. So the mode solver is going to be more accurate the higher the resolution is. So we're going to keep it at 100. Okay, so we have our eigenvalues, which are just the wave number k. We have the effective index from those eigenvalues. Now let's look at the actual electric and magnetic fields from the waveguide modes. So to get the electric field for a given mode number, so we're going to stay inside this loop here, and we're just going to say E is equal to ms.getE field, and then you tell it which band you want that E field at. And we don't need the +1 anymore, so I'm going to get rid of that. Similarly, you can get the magnetic field using getH field, and again, we get rid of that +1. And also, you can get the pointing vector, which is cool. There's a lot of different fields you can get, and it's all just ms.get underscore whatever field. So yeah, just check out their documentation if you want to get any sort of obscure field. I think you can also get like the electromagnetic energy density. But yeah, okay, so these electric and magnetic field arrays are quite large. So they are 4-dimensional arrays. So if we wanted to look at, let's say, just the X electric field, we would say something like this. So EX is equal to E at colon, colon. So again, our simulation domain is just in the X and Y direction. So that's why we have colon for the first index and colon for the second index. So the first index is just the X, second index is just the Y. The third index is the Z direction, but our simulation is just a 2D cross section, so there's 0 index there. Finally, the last index is the electric field polarization. So for EX, we keep that to be 0. But let's say if we wanted EY and EZ, then we can have 1 and 2. And so the 2 just means EZ, and the 1 just means EY. Okay, and so let's plot the EX field. So to do that, I'm just going to uncomment out this plot here. So we have a plt.contourf. Again, we're using that contourf function. We already calculated the x and y dimensions with the permittivity. So the electric field, so I'm going to call it EX. This EX array is going to have the same dimensions as the epsilon array that we had above there. So we can use the same x and y as with the plot that we made up here. Okay, now EX is going to be a complex number. So I'm just going to look at the absolute value, the complex magnitude, of that, np.abs. Just for contour F, I'm going to say use 202 different colors. And then for the color map, I'm going to use the seismic color map, which I define up here. So CMAP is equal to CMAP, and I set CMAP to be seismic. And that's just it's a blue to red colorful color map that I like. Labeling the axes X and Y, and I'm going to call this EX underscore mode num. Again, we don't need the +1 anymore, .png. Okay, so let's run this. Yeah, so it's going to take a bit of time there to calculate all those modes, but so again, this is what we're simulating. Oops. So just again, a silicon core surrounded by a glass cladding. And there we go. Now we have our electric fields. So this is the electric field for the first mode. So this is that EX field. The aspect ratio is wrong here because it shows the X and the Y to be the same size. But the X is 3 microns and the Y is 2 microns, so they shouldn't be. But anyway, this is what the electric field looks like in this silicon waveguide. So we can see that most of the electric field is confined in the center of the waveguide. And of course, we have these little lobes outside of the core of our waveguide. But yeah, and then as we go away from the waveguide, the electric field goes to 0. So the light is confined to that core region. And then we can look at the second. So this is the EX field for the second mode. So it kind of looks a little wonky there. And this is the EX field for the third mode. And also looks a little bit wonky. And you can see here that the third mode doesn't seem to be as well guiding because the field really goes off. The field really penetrates into the glass region. So it's not as confined to the core. So the better the confinement is, the better the waveguide. So for this particular waveguide, we'd probably want to stick with this fundamental mode because most of the light is confined to the core. So as we get away from the fundamental mode, more and more light leaks away from the core. So yeah, that's how we plot the electric field. And yeah, we could also do the same thing with the magnetic field, which I kind of show here. Here I just plot the magnetic field intensity, so hx squared plus hy squared plus hz squared, and we could plot that. I won't do that right now. And if we wanted to look at the pointing vector, so which is just the intensity profile, so we'd be interested in the pointing vector in the z direction. So we have pz, and that is just equal to 0.5 times numpy.real. So we want the real part of that pointing vector. So again, if you ask for just get pointing, it's going to give you this complex number. To get the actual real value of the intensity, you need to take the actual real. And yeah, to get the z component of the pointing vector, you just need to give 2 as the last index. All right, and then we're going to plot the pointing vector down here. So we have PLTL contour F. Again, x, y, pz dot transpose. Same color map, same jazz. Okay, and then there we go. I don't know why I have pointing underscore 2. We don't need that. Also, we don't need the +1 anymore. All right, and let's run this again. All right, there we go. You can see it's plotting the pointing plots here. So let's look at pointing underscore 1. Yeah, so this is what the electric field intensity looks like for the fundamental mode of this waveguide. And you can see that all the electromagnetic energy is focused inside the center of the waveguide. This is for the second waveguide, for the second mode of the waveguide. And here we can see that a lot more of the electromagnetic energy is starting to spread outside of the waveguide, so the mode is less confined. And finally, pointing 3, I'm going to need to actually explicitly open. Pointing 3. Yeah, pointing 3, a lot of the light has left the waveguide, so it's less confining. Okay, so yeah, this is how you use MPB. And as a last sort of thing I want to talk about, sometimes your waveguides aren't going to be perfectly rectangular. So sometimes you're going to be working with some sort of fab that'll have waveguides with these sort of sidewall angles that you see here. And typically this is like an imperfection from the fab process that they can't seem to get rid of. So if you want to simulate a waveguide with sloped wall angles, you could always just use the Meep prism object. So here I took my code and I commented out that core block that I had before, and I'm just going to use the meep.prism object here. And here I set the vertices. I set 4 vertices to define this sort of trapezoidal shape. You have to give it a height in the z-axis, even though we're not simulating a z-axis. Again, you have to define, you give it the z-axis, and you have to give it the material core. But once I run this script, so I'm going to let that run. If I open up my folder, here if we look at epsilon, here, yeah, so this is what we're simulating here. We're simulating a waveguide with sloped sidewall angles. And again, we have the same silicon permittivity on the inside and the silicon dioxide permittivity on the outside. Okay, it sounds to me like the simulation just finished. And yeah, it did finish. And here again, the first 3 modes, The effective indices are 2.68, 2.08, and 1.80. So let's look at those electric fields. So this is the EX field for the first mode. So yeah, you can see it's now a sloped sidewall waveguide, but still there's a good well-guided mode here. This is EX for the second mode, and this is EX for the third mode. And here's the pointing vector for the first mode, pointing vector for the second mode, and the pointing vector for the third mode. Okay, so there we go. This is all I really care to show you guys about MPB. Now you can use MPB to solve waveguide modes. So now that we're done with MPB, we can now return back to FDTD. Here we go. So now we're going to talk about waveguide simulations in FDTD. And to do that, we need to talk about two additional details. Eigenmode sources, which is just a source for waveguide simulations, and the Eigenmode expansion monitor, which is just a monitor for waveguide simulations. So right, as I said, the Eigenmode source, just a source for simulations. They usually will let the user define what mode they want, so n, what mode index n, and the frequency of that mode. You then choose the source plane location. So here we're back to using y as the propagation direction. So we have to define some y naught where to place our source plane. And then in the background, the Eigenmode solver is going to calculate the En at xz and Hn at xz in this red cross-sectional area. So just like we did with MPB, the Eigenmode solver in FDTD will do that same calculation. Finally, in the FDTD simulation, the source is going to be given by that mode field, these En xz for the n that we chose, multiplied by some sort of pulse source, so some sort of function of time, which again, we usually use a modulated Gaussian. So our electric field source at x, y naught, z, and t is just given by the mode profile, En at xz, multiplied by that function of time, by that modulated Gaussian function. And that's it. This is what a mode source would actually look like in an FDTD program. So hopefully one day, once I get to doing the 2D, write your own 2D FDTD code in Python, we'll actually do some mode sources as well. Because they are quite simple. It's just basically like a plane wave source, but you multiply by this mask. I was going to call these En and Hn kind of like a mode mask. Okay, so that's what an eigenmode source is. The Eigenmode expansion monitor might be a little more complicated in concept, but essentially it's going to calculate an overlap integral of the electric field in your simulation, E at x, y, z, for some plane along the y-axis again. So for some y equal to y1, it's going to do a mode overlap integral of this field here with the mode field En at xz for, again, the n of our choice. So this overlap integral will basically kind of tell us how much of this electric field is made up of this mode field. So if our if our FDTD simulation is just a straight waveguide with a mode source and a mode expansion monitor, then we'd expect that the overlap integral should be maximized, right? All of the electric field in that simulation should be in the mode that we injected with that mode source. Okay. So that mode amplitude, that overlap integral, gives you what is called the mode amplitude. So the mode amplitude for the nth mode as a function of frequency is just given by the overlap integral of the electric field in our simulation at that y1 plane at the frequency omega, again overlapped with the mode field En at xz omega. So that's a little bit more complicated. Definitely, if you're interested in learning more about that, Meep actually has some documentation on the Meep. Sorry, read the docs. They have some documentation on the mode decomposition. Do they have a picture of the integral? Yeah, so the integral looks something like this here. But yeah, I won't go deep into it. Just know that they do have documentation on how that overlap integral works. What's cool about a mode overlap integral is that it's directional. So uh, by changing the way that we define the mode field, we can actually determine how much of the electric field E is traveling in the forward or backwards direction. So we can calculate the mode amplitude for forward traveling light and backward traveling light, which is quite handy. And then using the mode amplitude, we can also get an estimate for the power carried by the nth mode in either the positive or minus direction. So here I'm saying for the positive y direction, the power carried by the nth mode is going to be proportional to the mode amplitude with the plus in the positive direction squared. So that means that for waveguide simulations, we can calculate transmittance and reflectance spectra using these mode amplitudes. So if we place a mode amplitude monitor at some location y1, then we can calculate the transmittance from y0, the source, to y1 using this formula here. So we have the mode amplitude at y1 absolute value squared in the positive direction, normalized by the mode amplitude at y0, so that's just in front of the source position, squared. And for the reflectance, we have the mode amplitude in the minus y direction, again in front of the source at y0, divided again by the source traveling in the positive direction. So notice here that the denominator for both of these expressions is the same thing. It's just what is the mode amplitude traveling in the forward direction right after the source. And then for the transmittance, we just need to know the mode amplitude that is transmitted through our system at some point y1. And for the reflectance, we just need to know what's the backward traveling mode at that y0 point. Right, so yeah, this is, again, so the numerator here is the forward traveling mode at y1, which is, again, further down our simulation domain. And the numerator over here is the backward traveling mode at y0. So for the reflectance, we actually only need one monitor. We just need that monitor at y0. All right, so that was pretty quick and easy. Now we're going to go back to our code, and we're going to now do a Meep simulation of a waveguide, and we're going to show how to plot the reflectance and transmittance using those mode decomposition monitors. So stay tuned. Okay, so now we're going to use Meep to run a waveguide simulation. So as with before, I have the code already written. It's commented out. So once again, we're going to be importing Meep, NumPy, Matplotlib. We don't need to call MPB this time around. So there we go. So the first thing we're going to do is we're going to set up our simulation domain size. So here I set up size X, size Y, and size Z. So because we're propagating along Y, I set Y to be longer than the other two dimensions. I'm also setting size Z to be 0 for now. So we're going to just do a 2D simulation to start with, just so that things run faster. Okay, next I'm going to set up the resolution. So I'm doing 25 cells per micron. I'm going to do a PML size of 10 FDTD cells. So the PML size is 10 divided by the resolution. And finally, the PML layers is just given by mp.pml. This is all stuff that we went through in the last Meep video. Next, we're going to set up our waveguide materials. So we need our core and cladding. So here are the refractive indices of silicon and silicon dioxide in the C-band. So the core medium and the cladding medium, they're just going to have a constant refractive index of n core and n clad. Next, the waveguide width and height, which before is going to be 0.5 width and 0.22 height. Now, the 0.22 height is in the Z direction, which is currently 0. So for now, with our 2D simulation, we're just going to see a 0.5 micron width. Okay, and now the waveguide is just going to be a block. So the block is just a rectangular prism centered at 0 with a width of W and a height of H, and it's infinite along the Y direction, which is the propagation direction. And finally, the material is set to be core. Right, so now we're going to set up the source and stuff. So first we need the source wavelengths. So the center wavelength of the source is going to be centered in the C band, so 1.55 microns. And then I have the minimum wavelength and the maximum wavelength, 1.4 and 1.7 microns. So the center frequency again, so in Meep frequency, it's just 1 over the wavelength. So center, minimum, and maximum frequencies. And then the frequency width is just the max frequency minus the minimum frequency. And we needed that so that we can set up our Gaussian pulse. So our... Okay, just do that. So pulse is equal to mp.Gaussian source. We give it the center frequency. We give it the frequency width that we defined. I multiply it by 2 just to make the pulse width shorter in time. Now we need to set up the actual mode source. So we need to give it a position. So I'm going to put the mode source at minus size y over 2. So this is one of the sides along y, one of the sides of the simulation domain along y, plus PML side. So I don't want the source to be in the PML, plus 0.1. So I want it to be a couple of cells away from the PML. So plus 100 nanometers away from the PML. Finally, the mode source. So to do that, we're just going to use these lines of code. Let me just uncomment them all. So here we have, again, we're going to put the source in as a list object. And we have mp.eigenmode source. And again, we give it as the first thing the pulse that we want. So that's just going to be a Gaussian pulse. You tell it where you want it centered. So I want it centered at x equal to 0 and y equal to, x equal to 0 and z equal to 0. And then y, again, I told it where I want it to be centered. The size, I'm just going to set it to be the size in the size x and size z directions. You could make it smaller than that, but for now, I'm just going to do this. You want to give it the propagation direction. So we want this mode to propagate along y. And then you need to give it the mode value, which is given as eigbound. So I'm asking it for the fundamental mode, the first mode. So yeah, that's the eigenmode source. Very easy to set up. And then finally, we set up our simulation object. And this is going to look like it did last time. We just give it the size of the simulation domain as cell size, the resolution, the PMLs, the sources, which is now an eigenmode source, and the geometry, which is just a waveguide, a Meep block. Okay, now I'm going to visualize the simulation space. So I do sim.plot2D. I have this output plane set up here. We don't need this for the 2D case because in the 2D case, it can just plot the 2D simulation domain. You only need to define the output plane for 3D, but I'm going to be using the script for 3D later on. So I have the output plane kind of set up preemptively. And finally, I'm just going to add a movie monitor to begin with. I know we want to add in those mode decomposition monitors in a bit, but let's just watch the movie to begin with. Keep it easy. So this is the same movie monitor as last time. I'm looking at the EZ field. I should say that in the current setup, the first mode is going to be primarily Z polarized for the electric field. So yeah, I'm going to be capturing the EZ field for the movie. And again, we have our run command here, which is the exact same as last time. I don't have translocation set up, so I'm just going to say size y divided by 2 minus PML size minus 0. So I'm just saying, like, wait till we're going to let the simulation decay, and I'm looking at the point far along the y direction near the end of the simulation domain. So I want the pulse to traverse the entire simulation domain before the simulation stops. And then after the simulation stops, it's going to make the movie. Okay, so now we can run this code. So I just called it Meep waveguide. So we're going to say Python Meep waveguide.py. Okay, so there we go. Now it's running the simulation. It's finished running the simulation. It's a 2D simulation, so it's quite quick. Normalizing field data means it's just making the movie for us. But while we're waiting for the movie to finish, I'm just going to pull up the folder. Sorry, let me just get rid of some stuff here. Yeah, sorry, let me just rerun this real quick. Here we go. So here's the folder. So here's that sim plot. So this is a plot of the simulation domain. So I'm going to open that up and bring it over here. So here, this is what we're simulating. So we have our waveguide running down the middle. So that's the black box, right? So that's our silicon waveguide. And then we have our PMLs all around the outside. So that's those green layers there. And then we have our eigenmode source, which is this red line. And it stretches across into the PML regions. Probably we shouldn't do that right now. I could probably cut it off. But again, for now, I'm just going to leave it as it is. So that's the simulation domain. I believe the movie just finished compiling. So let's let that run. Oh, it opened off screen. So let me just pull that in here. So here's our simulation domain. So again, around the outside, we have our PMLs, we have our waveguide, and then we have our source. And we should see our waveguide mode traveling through. So there's our pulse. So again, it's a pulse in the shape of a waveguide mode, and it's going to just travel across and then get absorbed by the PMLs. Awesome. Okay, so now that that's done, now we can start adding in more complicated monitors. So the first thing I'm going to do is I'm going to get rid of the movie monitor, just because that takes up a bit of time at the end of each simulation. So let's just delete that for now. Get rid of that. I'm now going to add in a DFT monitor, a discrete Fourier transfer monitor, and that's going to look like what it looked like last time. So here I am defining a vector of frequencies that I want the DFT to be calculated at. So that's just 1 over the minimum wavelength, 1 over the central wavelength, 1 over the maximum wavelength. And then I'm asking for it to DFT the EX, EY, and EZ fields at those frequencies centered at 0, 0, 0. And then the size, so it's going to span the X and Y direction, so we can see the propagation direction. And then to plot those DFTs, again, we're just going to use some similar code from last time. I'm just copying and pasting from off screen. And it's after the sim.run. We have this. So it's a little more complicated than what it looked like last time, but let's just go through it. So here we're looping through our DFT frequencies. So again, that's just a list of 3 frequencies that we're evaluating our DFT at. So we're going to loop through those frequencies, and at each frequency, we're going to get the EX, the EY, and EZ field in that DFT monitor. So this is the same. So we saw these functions last time. I believe last time I only did the EZ field, but now I have all 3. And I'm going to plot the EX and EZ field, just the real parts of those. And this is the same plot function as I used last time. So that's our DFT monitors. I'm not plotting the Y field just because the mode is propagating along Y. So the electric field in the Y polarized electric field is going to be quite negligible. So I'm actually going to just get rid of that for now. So we don't need that. And also to save computation time, we can get rid of the mp.ey in the DFT field command here, because we don't need it. And then we want our mode monitors, our mode decomposition monitors. So for that, Meep it repurposes the flux monitors. So I'm going to copy some stuff from off screen. So first things first. So actually, first things first, let me just put a comment here, DFT monitor, just to have good code. And then we're going to have our flux monitors for mode decomposition. Okay, so our flux monitors, I'm going to look first, I'm going to put our incident flux monitor. So if from the slides, that was the Y0 flux monitor, and that's going to be in front of our source. So that's the source position plus 200 nanometers. So plus just a small buffer. And then the transmission location is going to be, again, at the size Y/2 side of our simulation minus the PML side. So we don't want to measure the transmission in the PML, obviously. So then we're going to give it a little bit of a buffer outside of that PML. Okay. I'm also going to just grab the plotting 2D guy here and place it down here. Okay, sorry. So now we set up our flux locations. Now we just need our flux monitors. And those look like they did last time. And we only need 2. So we need one for the incident plane. So this is the one that's in front of our source. So again, we're going to add flux we're going to calculate the fluxes at these frequencies. I haven't defined freaks yet, the frequency array. So I'll do that in a second. But here is where we define, this is where we place the flux monitor. So it's going to be centered at some location along Y at ins location. So that's just what I defined here. And it's going to have the size of the X and Z dimensions of our simulation domain. Similarly, trans is almost the exact same thing as inst, but it's centered along Y at trans location. Right, I need to define these frequencies here. So I should have done that first, but oh well. So I'm going to define a vector called monitor wavelengths. So these are the wavelengths that I want to calculate the mode decomposition at. So that's going to be between min wavelength and max wavelength with 31 wavelength steps. And again, the frequencies is just 1 over those wavelengths. And those frequencies are what are plugged into the add flux command. Okay, so now we have our flux monitors. Now we need to do the mode decomposition. So the simulation finishes, and I'm going to go with here, do mode decomposition. This is where things might get a little messy, but that's okay. I'm going to copy and paste the code from off screen. So first we're going to use this command here. So it's sim.get eigenmode coefficients. And we're going to be doing this for the transmission flux monitor. So we give it trans, which is again just our transmission monitor here. We tell it which modes do we want it to do the overlap integral with. So because I sent in mode 1 up here in the source, I'm only going to ask for mode 1 down here. I can also ask for 2 and 3 and all that stuff, but they're not going to have, it's going to be negligible values there. So I'm just going to ask for 1. And again, I'm giving it the direction mp.y. So that's the propagation direction. And I'm also going to do the same thing here, but for the incident monitor as well. So ints. Great. Okay, so now we want to get those mode amplitudes that I talked about in the slides, those alphas. So for that, I'm going to start with the incident mode amplitude. So I'm going to call that A ints. So A is for alpha. And it's going to be ints underscore dot alpha. So they also call it alpha. All right, so then there's 3 indexes for alpha. So the first one's going to be 0, the second one's going to be a colon, and the third one's going to be a 0. So the first index is what mode, right? So I set up here for ints here, I'm asking for the first mode, but I could have asked for the second, third, and fourth as well. So if I ask for multiple modes, then I can put in multiple, like I can ask for which one of those modes here in that first index. But since I'm only asking for the first mode, I only get to ask for 0 here. So that's what that 0 means. The next index represents the wavelengths. So I want to get the alpha for all the wavelengths. So that's why there's a colon here. And finally, the last index could either be a 0 or a 1. So for forward traveling waves, we want it to be a 0. For backward traveling waves, we want it to be a 1. So remember what I said before in the slides. The eigenmode amplitudes are directional dependent. So we can actually extract how much, we can actually just extract, the mode coefficient for forward traveling light and for backward traveling light. So for the incident guy, we just want the forward traveling light, so we put in a 0. Same thing for the transmission. So for a tran, or I'm going to say AT, we're just going to go trans.alpha. And again, same guy. So we only have one mode, so 0, all the wavelengths, and again, only forward traveling. So for the reflection alpha, so for AR, things are going to be a little different. So here again, we're using the incident monitor. So we're going to use the incident monitor for both the incident measurement and the reflected measurement. So to get the reflection, we just need to set this guy now to be 1. Because the reflected light is just the backward traveling mode. Okay, and then to get our transmittance and reflectance, so let's just say calculate transmittance and reflectance. we're just going to use the equations from the slides there. So that's just np dot absolute value of at to the power of 2 divided by the absolute value of the incident alpha to the power of 2. And same thing for r, just put AR in the numerator. And then we're going to plot all that. So calculate and plot. Okay, and now we're going to go with plt.plot monitor wavelengths. So that's going to be our x-axis and t. And I'm going to plot the transmittance in red. And for the reflectance, R, and we're going to make that blue. And then I'm going to plt.x label wavelengths in microns. Plt.legend, right? Because there's 2 lines, so we want a legend, make it a good plot. So T and R. And we're going to now save it, save fig, and we're just going to call it tr.png. And we're going to plt.close that. So we are using these flux monitors as our eigenmode decomposition monitors. After the simulation runs, we then get the eigenmode coefficients for those 2 flux monitors. We then extract the alphas using these lines of code, and then we can calculate the actual spectra using these lines of code. And now we're ready to run our simulation again. So let's see. Yeah, of course. Right, because I got rid of the animate, so I'm going to get rid of the animate from the sim.run call here. So there we go. Now the simulation is running. All right, so because it was doing a bunch of eigenmode decompositions, you're going to get all of this stuff popping up here. And you can see here it's using MPB in the background to do those mode decompositions. So that's neat. All right, so now let's look into our folder. Where is the folder? There it is. All right, and now we can see our electric field plots for the minimum wavelength, the maximum wavelength, and the center wavelength for EX and for EZ. We have our simulation domain plot here, which is just this guy here. We've seen this already. Oh, let's look at this here. So here we have our simulation domain. It looks like it did before with the waveguide running through it. The red line is the source, and it's just outside of the PML region down here. And here we have this blue line just in front of the red line. So this is our INS monitor. That's that INS flux monitor. And then up here, outside of the PML, in the far Y region, you can see another flux monitor here, this blue line. And this is the transmission monitor. So that's where those are in the simulation domain. And now we can look at the TR plot. So this should show us, perfect. All right, so here the red line is T, so that's our transmittance. And you can see that the transmittance is 1, right? So all of the light that we injected into the waveguide exits through the back end of the waveguide. So it all went through. There was no obstructions, so the transmittance is run. And since there was no obstructions, there's no reflection happening, so the reflectance is just 0. And we can look at those Fourier transform monitors here. So since we were doing the fundamental mode for a 2D waveguide, the electric field is going to be primarily polarized in the Z direction. So let's look at the Z fields there. So this is at 1.4 microns. This is what the electric field looks like. So you can see we're injecting the electric field down here in the minus Y region. And then all the way over here is where we calculate the transmittance. So here's 1.7 microns. So it kind of looks, so 1.4, we have small wavelengths. 1.7, we have slightly bigger wavelengths. And this is the fundamental wavelength. This is at 1.55 microns. Okay. And then if we look at the Z fields are going to, yeah, so the Z fields look messy. But you can notice here it's 10 to the minus 8. The Z, sorry, the EX fields. This is the EX fields. They look messy just because the EX fields are negligible for the fundamental mode for this waveguide. And you can tell just by the magnitude of the field, 10 to the minus 8. So, and we'll see that for all wavelengths. Yeah, the X field looks ugly, and the Z field is where the mode actually is. Okay. So, let's see. Yeah, so stuff that you could play with. You could also go to the source and do the second band. So let's do that actually. So we're gonna do the second band. Over down here, I'm gonna ask it now for the first order band and the second order band. Let's do that. And yeah, I'm gonna do this. So I'm gonna copy and paste the alphas. I'm gonna have alpha 2 for the second band, alpha 2, alpha 2. And here, now I can ask for the 1 index. Okay, and now, so I'm going to do plot T2 for the second one, and that's just going to be a T2, A2, there we go. Okay, so now I'm plotting, so I'm going to be injecting light into the second band, but I'm going to be doing the eigenmode decomposition for the first and second band, and then I'm going to calculate transmittance and the reflectance for the first and second band. So what we should see this time around is that the transmittance for the first band is going to be 0. The reflectance for the first band is going to be 0 because I didn't inject any of the first order mode. And then we're going to see a 1 for the transmittance in the second order mode because that's what we're injecting in. And again, a 0 for the second order reflectance because we're not expecting there to be any reflection. So let's plot that all again. So this time I'm going to do, so x2 I'm going to plot with x's, but again, red. So x, I'm going to say color is equal to red. And then for R2, I'm going to do blue, but with x's, just so we can distinguish all these guys. So it's T, T2, R, R2. So let's just update our legend. T, T2, R, R2. And again, the 2 just means that it's the second order mode. And let's run this again. There we go. Okay, so let's look at our TR plot this time. Actually, first let's look at our electric fields. So now the Z fields look something like this, and they're quite small, right? 1e minus 9. So the Z fields are small this time, and the X fields, this time the X fields are dominant. So this is the EX field at 1.55 microns, EX at 1.7 microns, and EX at 1.4 microns. So with the second order mode, the EX field is dominant and the EZ field is negligible. Now let's look at that TR plot. Oh, that's interesting. Sorry, it took me a second there because this is not what I expected. What I expected was the solid red line to be 0 and the X's to be 1s, the red X's to be 1s. The reflection is what I expected. So what's actually happening here is that we're getting 1 transmittance for the first order mode, even though we're not injecting the first order mode. But here's the thing. Because we're doing a numerical simulation, there is always going to be a non-negligible amount of that first order mode. And that's a little weird. It's a little weird to think about. But there's going to be a very small amount of that first order mode that is injected, even though we're not asking it to be injected. It's just like a numerical error. So what we can see is that that numerical error, first order mode, also propagates losslessly through the waveguide, even though we didn't ask for it. So that's why we get a 1 transmittance for that solid line. So if we want to do a fair comparison, if we want to see how much of that first order mode, like what's the fraction of that first order mode, then for our T, we're gonna want to normalize our T and our R by A ints 2 rather than A ints. So the reason why we're doing this is that we're injecting light now into that second order mode. So that denominator for all of these measurements should be that second order power. So if we run this again, we run it again. This time we'll see what I expected the first time. So yeah, here now we can see that the first order transmittance is pretty much 0, again, because we're not injecting any of the first order light. But the second order transmittance, the second order mode transmittance is 1. Okay, so there we go. Oh, some behind the scenes footage there for you. Okay, so that is how we do a waveguide simulation in Meep. Before I move on, I'm just going to redo this simulation, but now in 3D. So this is going to take a little bit longer, but it should be interesting to see. I should add the movie back in. It's not really worth to put the movie back in. But what I will do is just do a cross-sectional plot here in the XZ direction now. So size Z 0. Okay. So now we have a sim XZ plot. So we can look at the XZ cross-section of our simulation. We're going to run it again. And I'm going to do the first order mode this time. So Eigenband with 1. Since we're injecting light now in a 3D waveguide, where the mode is the first mode, we're going to expect that the light is going to be polarized primarily in the X direction. But we'll see that when we look at the field plots. Okay, so I'm going to run this simulation, and I'm going to pause the video because this is going to take a while to run. Okay, so the 3D simulation finished, but before we get there, oops, close that. One thing, I made a little mistake before I cut the video. Just make sure, if you're following along with the video, make sure in the denominator of these T's and R's, you go back to A-ints, because I forgot to do that before I cut. So anyway, so I corrected that mistake, and then I reran the simulation, and now we can look at the results. So I'm going to look at the Z electric field from those DFT monitors. Oops. Not Z, sorry, the X electric field. Yeah, so this is what the EX field looks like at 1.4 microns. This is what the EX field looks like at 1.7 microns, so just a larger effective wavelength. And EX at 1.55 microns. So it looks like the 2D simulation, only it's in 3D. And this is what the EZ fields look like now. So the EZ fields are very small, but yeah, they're not actually, they don't seem to be guided well. But the main electric field is the EX field for this polarization. And we can look at the TR plot again, and we can see that our transmission is 1 for the first mode, as expected. Okay, so that is a 3D FDTD simulation of a waveguide. And before the video ends, I just wanted to do one more thing that's a little more interesting. I want to do waveguide bends. So suppose you have a waveguide and it's traveling in the Y direction, but now you want it to travel in the X direction. So you need to do a 90-degree bend. So how do you do that? So I wrote up a little script here called Meep waveguide bend. If we open it up. So this is very similar to the last script. Only if we go down to the geometry, you'll see I added an extra waveguide and these 2 wedge objects. So the first waveguide is our original waveguide traveling in the Y direction. Only instead of being the full simulation domain size, it's now only half of the simulation domain size in the Y direction. And it's offset in the X direction by a little bit. Similarly, we have another waveguide, but this time this is the outgoing waveguide. So this one is pointing in the X direction. And then these 2 wedges here, these are like cylindrical wedges, and they make the waveguide bend region. So I'll show you what that looks like in a second. But this is our new waveguide bend geometry. Okay, the source remains pretty much the same. It's going to be traveling in the Y direction. We're just offsetting, again, that X position there so that it aligns with the waveguide. We have our simulation object, our DFT monitors. We have, our flex monitors here for the mode decomposition. So the incident monitor saves roughly the same. Again, we're offsetting it in the X direction. The transmission monitor, however, now the mode's going to be traveling in the X direction for the transmission. So we had to kind of flip that flux monitor But you can look at all these parameters here and you can see what we did. We're going to plot the domain so we can see what everything looks like. And then we're going to run our simulation. So then we're going to do our mode decomposition afterwards. So for our trans, things are pretty much all the same, except for the direction is now mp.x. For the incident, this line here remains the same. Our alpha coefficients here are just these guys here. Our transmitted light is actually going to be traveling in the x direction, but in the minus x direction. I'll show that in the plot in a second. So that's why there's a 1 here. Sorry for that being confusing. I should have set it up differently, but anyway, the light will be leaving the simulation in the minus x direction, so you need to put a 1 here for that AT. But again, you can calculate the transmittance and reflectance using the same calculation here and output the DFTs. Okay, so now we're ready to run this simulation. So here I'm in my waveguide bend folder, and I'm just going to run the Meep waveguide bend file here. And I'm going to open up that folder, and we're going to look at that sim. So this is what that simulation domain looks like. It's a 14 micron by 14 micron box, so pretty big. Our incident waveguide is this one that goes up here in the Y direction. You can see it then makes this 90-degree bend here and then out into the X direction, in the minus X direction to be exact. So here we have our source. You can see our Eigenmode source. And I said that the input waveguide and the source and the monitor have to be offset in the X direction. Well, this is why. You can see it's no longer centered at 0 in X. It's now centered at like 4.5-ish. That light gets injected, goes through the 90-degree bend. And then here's that output flux monitor, which is now capturing light traveling in the X direction. And again, we're going in the light's going to be going in the minus X direction. So we needed that 1 in the alpha coefficient here, as I mentioned. Okay, so the simulation ran. So let's take a look at the fields. So this is the EZ field. So you can see light's going to come in, it goes around, and that light, it's not exactly, you can see it's not entering that mode, that outgoing mode cleanly, right? There's a bit of a zigzag happening here. Is there anything to look at in this? This is the X field. Yeah, there's nothing much to look at here. And if we look at the TR spectrum, so yeah, we can see that in the reflection spectrum, there's no reflection happening. But in the transmittance, we can see that there is only 70% of our light is getting transmitted. So there's quite a bit of loss in that 90-degree bend there. So in order to make that loss smaller, actually first let's make the loss bigger. So let's make the bend radius smaller. I'm going to go down to, let's say, 2 micron bend radius, and I'm going to make the simulation domain smaller. Let's see how that affects the transmittance. So let's run it. You can look and see now it's a smaller bend radius. So we can expect that there's going to be a lot more loss. So the simulation finished. And yeah, so now we can see that the loss is now closer to 50-60%. Sorry, the transmittance is closer to 50-60%. So yeah, that's not a good waveguide bend. So this is why when you're doing silicon photonics, they always tell you to use a bend radius around 10 microns. So let's do that. So let's see. How big does... We're going to do a big simulation here. Let's see. Is this big enough? I suspect not. No. Ooh. Okay, so let's make it 24 by 24. All right, that's roughly big enough. Yeah, that's pretty big. That's pretty good. So let's let this simulation run. I'm going to do a cut here just because I think it's going to take a bit. And here you can see there with that 10 micron radius that now we're up to closer to 90% transmitted. So things are getting better. So we probably need a bit of a larger bend radius to be comfortable, especially if we're going to have a lot of bends on our photonic circuit chip. But anyway, this is This is how you would simulate a waveguide bend using Meep. And what you could do is, if you're interested, is you could wrap this all in a for loop, right? So I can say radii, and make a loop of radii, then space, and I'm going to say, let's say between 2 to, for now, let's go 2 to 6 radii with 11 steps, and you could say for r in radii. Maybe we do something like that. Wrap it all like this. And then radius, we'd set that to be r. We would set this to be, let's say, r times 2 plus 4, let's say, plus 5. Sure. Anyway, we could run a loop like this, and then we could calculate how that transmittance changes as a function of radius, and from there figure out like what's the ideal bend radius for our simulation. That's kind of the beauty of doing these simulations in Python, from my in my opinion. But anyway, yeah, that's it for this video. This has been computational nanophotonics videos. Today I walked you through how to use Meep and MPB for waveguide simulations. I hope you guys found this enjoyable and useful. Yeah, make sure to like, comment, and subscribe. And have a good one. Bye.